Okay, good afternoon, everyone. So today I want to do an example of the load line analysis technique. As a brief recap, let's bring up the load line analysis. This is a very important technique because we will use this again for Zener diodes, we'll use it for BJTs, we can use it for FETs, MOSFETs. It's a graphical analysis technique that allows us to determine the Q point. So as a recap, Q point stands for quiescent. Quiescent simply means dormant or lying in wait, prepared. So the Q point is a result of a application of a DC voltage to your circuit. So you have a diode, BJT, transistor, Zener diode. You apply DC voltages to it, and it sets up the device to operate within a certain constraint. Okay. So the Q point is basically the result of the external constraint that is put on the device by the external circuit. In this case, the external circuit is the voltage source and the resistance. Okay. So because it's a graphical analysis technique, we are trying to solve for diode voltage and we are trying to solve for diode current, ID. So two unknown variables, we need at least two equations to solve for them. So the first equation in this graphical solution comes from the device characteristics. Device characteristics are not going to change, right? Depending on the fabrication, the characteristics might shift by a few microvolts or microamps, depending on the design and the doping profile. But the characteristics are so-called because they would be pretty much the same for all devices. So diode characteristics are going to look like this, right? The only difference would be in the voltages and the currents. So we have one equation, and this characteristic is based on the diode equation, right? We need a second equation, so we need a second graph or a second plot, and we obtain by applying KVL to that circuit. When we apply KVL to the circuit, we get an equation in terms of the diode current and the diode voltage. Since we are describing this as a linear line, it will intersect the X and Y axis at two places. Sorry, not two places, at one place each, right? It's going to intersect the X and Y axis at one particular point. Intersection of the X axis is when Y is equal to 0. Intersection of the Y axis is when X is equal to 0. So to determine those coordinates, we simply plug in ID is equal to 0 and VD is equal to 0. Once we determine those 2 points, we join the line. Sorry, we join the 2 points to obtain the line. The line is going to intersect the diode characteristic. The intersection point is the Q point. Intersection point is the Q point. The coordinates of that Q point, extrapolate the Q point on the X and Y axis. Those are the solution to those two plots. The coordinates, the X coordinate gives us VD, Y coordinate gives us ID. Did everyone understand that? This is what we covered last class on Wednesday. So this is a recap. And then let's look at the example. In the interests of saving time, my annotations are already on here. So they are already available to you at your end. Right. So we have a circuit comprised of one voltage source, V battery. That's all it. And that V battery is 12 volts. Right here. And it's connected to the diode via a network of 4 resistors. R1, R2, R3, and R4. Okay. So Unlike the circuit that we not analyzed, unlike the circuit we saw just a few slides ago, this circuit needs to be reduced. Okay, we need to determine the voltage that is being applied to the diode and the resistance that is connected. So we need to simplify the circuit to its Thevenin equivalent circuit. Okay, we need to go from here to here. Once we do that, we can apply KVL and we can determine the 2 points for that line. Does that make sense to everyone and what we are trying to accomplish? So pretty much any device we take, whether it's a Zener diode, BJT, common emitter CE amplifier, if you perform a load line analysis, the steps are exactly the same. You have a large linear network, large linear circuit that is connected to a nonlinear device. We need to determine the exact voltage or current that is being applied to that device. And to do that, you have to call on Thevenin and Norton. In this case, we don't have to worry about Norton circuit, just Thevenin. Okay, so if you want to determine the Thevenin circuit for a component, we have to remove that component from our analysis, which we do here. That leaves behind open terminals, and we analyze the circuit between those open terminals, A and B. Does everybody remember Thevenin circuits? Hopefully. We did it in what, 115? Okay. So you are all experts in that, hopefully. It's a very important theorem. Okay, any kind of analysis, circuit analysis, it's a very important theorem. All right, so we need to find 2 quantities. All right, so at this point, all we are doing is we are simplifying the original circuit down to 1 single voltage source and 1 single resistance. That's all we are doing in this step. Okay, so to determine Thevenin voltage, the circuit, sorry, Thevenin resistance first. What do we do with the voltage source? Anyone?
We replace it with an open circuit.
Well, we replace it, yes. I would say both answers are correct, but like halfway correct. So we don't short circuit. No need to laugh. It's just explanation. So yes, we place a short circuit, but we don't short circuit the source, and we replace the sources. So the point is, if we want to find resistance, we need to get rid of everything in the circuit except for the resistances, right? So all the sources that are there in the circuit, we replace it with something. Voltage sources have very low resistance, almost amounting to 0. So we replace an we replace a voltage source with a short circuit, and we replace a current source with an open circuit. So in this case, because we replace it with a short circuit, what happens? Now the 50 ohm resistance is in parallel with the 10 ohm resistance, and then those would all be in series with the 20 ohm resistance. And so we can find RTH between those terminals as 48.3333 ohms. Yes, you can perform a source transformation, but that would be kind of make it, well, I wouldn't say complicated, but it wouldn't serve any purpose in this instance. So if it makes our job easier, then yes, we can use source transformation. But in this particular case, I don't think it would help. I guess if you use source transformation, we can have a current source in there. We replace it to Norton. We'd still have to apply a current division to determine the diode current. So the number of steps would be pretty much the same. But yeah, that is something we can use. All right, so that was Thevenin resistance, Thevenin voltage. What happens to the voltage source in the Thevenin voltage? Anyone? Now you can laugh. Nothing happens to it. I mean, we need voltage source. If there is no source, we don't have any output. So the circuit stays as it is. If there was a current source there, we'd leave it as it is. If there's a voltage source there, we leave it as it is. Without a source, we don't have any output. All right, so VTH. Okay, VTH. Here's the important thing. The 20 ohm resistors are not connected to anything. Okay, so I'm going to explain this. Let's go down here. If you have a resistor that is connected to a circuit, but the other end of the resistor is open and not connected to anything, what is the voltage? What is the voltage drop across that resistor? 0, because current needs a pathway to flow through. If the resistor is open, there is no current flowing through. All of the current is coming from the supply and goes down here, right? There's no current flowing through that open resistor. If there's no current flowing through the open resistor, the voltage drop is 0. Voltage is nothing but the difference in electric potential between any 2 points. If there is no difference between the 2 points, then we have voltage equal to 0, which means if voltage V is equal to 0, if V is equal to 0 here, it means both ends of the resistor are the exact same electric potential. The resistor may as well not be part of the circuit, or may as well not be connected to the circuit, because there is no current flowing through. The resistance is not opposing anything. Important concept. Okay. So if you want to find VTH, it's the same as this point. And so that's what the circuit boils down to. All right, let's take a pause while you think over all of that and let me know if you have any questions. Does that make sense? Any questions from anyone? Any questions? Okay. So what can we say about these 2 resistors that are left? They are in series. If they are in series, then the voltage that is applied to that series resistance connection is divided. So we can apply voltage division principle. And it's voltage division principle. Is that something you studied in 115? Perhaps. Okay, that's good. So 12 times 10 over 60 gives us 2 volts. So the diode is seeing an application of 2 volts as the source because it's being broken down across 4 resistors. So by the time it reaches the diode, it's already down to 2 volts. Okay. So now we can replace this circuit, and this VTH becomes 2 volts. This RTH becomes, what is it? 48.33. That is what the diode sees. It sees the 4 resistors as a single resistor of 48.33 ohms, and it sees the 12-volt source as a 2-volt source. Okay. That's why Thevenin and Norton circuits are important. It allows us to quickly determine what voltage and current is being seen by a particular component. Yes. For this step, okay, so question being asked is how is that equation determined? So we have a short circuit on the far left. So this is 50 ohms, this is 10 ohms, this is 20 and 20. The 50 becomes parallel with 10. And then if we reduce that 50 and 10 in parallel, it is now in series with the 20 ohms. Other questions? Okay. So now that we have that, we apply KVL. We apply KVL to this circuit loop, as we saw in the 2 slides ago. So we have KVL, VTH is equal to the voltage drop across the resistor plus the voltage drop across the diode. So diode VD and ID times RTH. VD is unknown, ID is unknown. So we replace ID and VD as 0 in turn and determine VD and ID. So if ID is 0, VD is 2 volts. If VD is 0, ID is 47.38 milliamps. Now we have 2 points that describe that line, that describe the linear portion of that circuit. You can go to the graph and we can plot those 2 points. First point is here, VD is equal to 2 volts. The second point is here, 41.41 milliamps. We join them, we get the line. The intersection point of the line is the solution using the load line analysis. Extrapolate that point to the X and Y axis, that gives you the solution for the diode voltage and the diode current. Diode voltage turns out to be 1 volt, as seen here, and the diode current turns out to be 21. That's the solution, graphical solution. One equation was from the diode characteristics that is already provided. The second one is we generated. This is known as the load line. That line describes the circuit, hence it is known as the load line. Okay. So this load line is the constraint placed on the diode by the external circuit. External circuit means the power supply and the resistors that are not part of the diode. Okay. If you change the values in the external circuit, it will still remain a line, but the line will shift up or down depending on your values. So as practice, you can plug in Vs is equal to 5, 10, 15, or 20 volts. You have all the equations. All you need to do is crunch the numbers. So you plug in the values in the equation, you obtain the Thevenin voltage, Thevenin resistance. Resistance stays the same because that's not changing. But the supply voltage is changing. So your Thevenin voltage will change. Because the Thevenin voltage changes, the line is going to shift either down or it's going to shift up. And for each one of those supply voltages, the Q point is going to be slightly different. Right? The intersection point is the solution for that particular supply voltage. Again, diode characteristic means the diode can operate within those parameters that's given by the manufacturer spec. But when we design a circuit, we can place a constraint on our device by the specific voltages we apply and the specific resistances that we connect. If we perform the lab today, or you'd be doing it tomorrow and Wednesday, we are going to experiment with BJTs. So we apply a particular DC voltage to our transistor. We are creating a circuit using some resistors. Those are constraints on the operation of the device. All right, so let's take a pause. Let me know if you have questions. Yes. So the question being asked is, would the load lines always be parallel if we change the voltage source? The answer is yes. Well, actually, in this case, let me see. Yeah, for the most part, they should remain parallel. Yes. Yeah. Unless we change the resistance also. I haven't done with these particular values, but if someone does, let me know if it doesn't turn out to be parallel. Any other questions? Okay, so the intersection point gives us diode voltage and diode current as 1 volt and 21 milliamps. From there, we need to find, the original question was, determine the diode operating point and the total power delivered by the source, the battery, the total power delivered by the source. So if we wish to find the total power delivered by the source, we need to find the power associated with every single component in the circuit. There are 4 resistors and 1 diode in the circuit. If we add up the power for all of them, that's when we'll find the total power delivered by the source. Now, with a diode, we already have the voltage and current. Alternatively, what we can do is just determine the total current that is being supplied by the power source. If we find the current through the power source, we simply apply our equation, P equals VI, voltage times current. But we don't have this current, IB. So we need to determine that current. In order to determine that current, we can apply KCL. There are a few steps we can take. We can apply KCL. We can write total current is equal to IR2 because it splits into 2 at this node. So you apply KCL at the top node, source current going down R1 splits into 2, IR2, and then it goes into R3. So obviously, the current going on the far right is all the same. That's the diode current because all 3 of them are in series. So it simply becomes IR2 plus IDQ. Right? That's the KCL current. But we only know one of those quantities. 2 of them are unknown. IB is unknown and IR2 is unknown. So we need to find IR2. If you want to find IR2, we can apply Ohm's law to R2. In order to do that, we need the voltage for R2. Thankfully, there is a way to find voltage across R2 because voltage across R2 would be the same as the total voltage across R3, across the diode, and across R4. R2 is in parallel with the 3 components to the far right. They share the exact same 2 nodes. When you take any 2 nodes in a circuit, anything that is connected between those 2 nodes will share the same voltage, because that voltage is a result of all of those components acting together or working together. So we can find, it's 3 o'clock. If you need to leave, you can leave. We can apply KVL to the far right. We can find VR2 is equal to VR3 plus VD plus VR4. We already know what VR3 and VR4 would be because we know the current. That's the diode current times 20 times 20. So 40 times 21 milliamps plus 1 volt diode voltage. We find VR2 as 1.84 volts. From there, we apply Ohm's law to find IR2. And once we have IR2, We simply apply KCL at the top and find total current supplied by the source IB. Once we have IB, power is V times I. We find the total power supplied by the source as 2.46 watts. Yes. Oh, that's the 21 milliamps. That's IDQ, the diode current. Okay. So we are in a rush at the end. So please review my notes. Again, these are already available to you. The video will be online shortly after I reach my office. So by 5 p.m. or so, review this before we come to class. Again, this is an important technique because we'll use load line technique again and again and again for the other remaining devices. And then prepare your questions so I can answer them on Wednesday. All right. So we'll end class here today, and I will see you all on Wednesday.